Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Adding structural effective primitives to Rotor in order to give a direct support to the primitives semantics or statements of dynamic languages. So dynamic modification of programs structure and behavior and runtime is an interesting and useful idea to develop adaptable and adaptive systems. A system is said to be adaptive if it can change its own behavior or structure at runtime by itself, and who modifies the system's behavior, structure, and runtime is the final user, then a system is normally said to be adaptable. There are different approaches to offer this adaptiveness or adaptability. First, by using specific languages who produce or give services of reflection that are mostly known as dynamic languages. We've got also adaptive paradigms and agile methodologies, and a lot of domain-specific frameworks. So we've worked in the first level, that is a programming language level. We can define programming languages like those languages that support reasoning about and customizing their own structure and behavior, supporting self-modifying features and dynamic code generation. So as a side effect of this dynamism, these languages offer a dynamic typing system. Different samples of what can be done with reflective primitives in these languages are changes the interface of the objects or classes, modifying implementation of specific methods at runtime, adapt the structure of objects or generate new code while the program is being executed, or modifying the type of object is instance of, or even customize the behavior of a set of classes by using the concept of meta class. These facilities offer the programmer many benefits and also drawbacks in comparison with static languages. Main benefits are, first, they facilitate the creation of adaptive and adaptable software. In many cases, it's said that this adaptive system could also be created with static languages, and this is mainly true, but if we use these kind of languages, it is much easier to create that code, and code is much maintainable and reusable. The second benefit is that design time and runtime are integrated, meaning that at runtime it can be produce new behavior, for instance, adding new business rules to an application. And finally, those languages make new entities first-class objects like classes, modules, functions, and so on, so the programmer may increase the parameterization in its code. So due to these benefits, static platforms are constantly including dynamic features inside of the implementation. About the drawbacks, there are two main drawbacks in these languages. First, of course, the lack of static typing that produces that the programmer should wait till runtime to detect some errors, and in other cases the compiler could detect. This lack could be in some sense overcome by using a test-driven development. For instance, in Python we can use the Python unit test suite. And also an interesting idea is try to mix the best of static typing and dynamic typing, that is that the programmer could use a static typing where possible and dynamic typing when needed. That is an idea that Eric Meyer has published in one of his papers. And finally, the most serious drawback, I think, that is performance, that is caused by inferring and checking types at runtime. So our project has tried to answer different questions. It's possible to improve runtime performance of reflective languages by using the just-in-time compiler of Rotor. It's possible to make static and dynamic languages interoperate one with another. And it is possible to combine the best of both worlds meaning that we can mix static and dynamic trapping when needed. So the main objective of our project has been extend Rotor with structural reflective primitives to evaluate the feasibility of making the CLI a platform to directly support reflective primitives of dynamic languages, and also to evaluate the performance cost and performance benefits of using the Rotor just-in-time compiler. So I have spoken a little about our project. I'm going to talk a little about reflection and how we have introduced structural reflection in Rotor, some details about implementation and the performance assessment, then the ending conclusions. So reflection is the capability of a computational system to reason about and act upon itself, adjusting to changing conditions. So reflective languages or dynamic languages that offer reflective primitives are those who enhance their domain with its own structure and behavior representation. So the programmer may inspect and in many cases even modify the running structure or behavior, and these changes are reflected on runtime. So regarding to what can be reflected, reflection can be classified into 3 levels. The first one is introspection, where the programmer could inspect but not modify the structure of programs. That is the level that is offered in Java and .NET platform. The second one is structural reflection, where not only the structure can be inspected but also can be modified. Python, Smalltalk, or Close are these kind of languages. And finally, the highest level of reflection is computational or behavioral reflection, where language semantics could be customized by the programmer. Many of the prototypes that implement this level of reflection are based on the meta-object protocol concept. So runtime adaptiveness has been an important issue that has been in some sense included in the .NET design. The first level of introspection services are included inside of the reflection namespace. We've got also generative programming services. So programs in .NET can create new programs by using the emit namespace. And also attributes that are declarative information can also be known at runtime by using the reflection namespace. So the next step forward in the reflection classification is adding structural reflection services to the .NET platform. As I mentioned, there are languages that offer these services like Python, Dylan, or Smalltalk. So adding these services to Rotor has made the CLI a platform to directly support reflective primitives of dynamic languages, has also made the most of its introspective services to create adaptable or adaptive software, has improved runtime performance of the system implementations because we use the fast just-in-time compiler, and finally offer a direct interoperability between any existing language and the reflective ones. So what we've done is extended Rotor with a set of primitives. First classification is field manipulation. We can modify fields of structure of classes at runtime, adding or deleting, modifying the structure of classes, and even we can modify the structure of a single object without modifying the fields of the existing instances at runtime. We can do the same with methods, dynamic addition, deletion, and updating of methods of a class, of methods of a single object. The implementation of new methods can be done by using the emit namespace or clone the existing ones. And the programmer may combine these services with the introspective one to create adaptable applications in an easy way. So our first motivating example is this code written in Python that uses a structural reflection. Here in the left, we can see a point class with a constructor, 2 coordinates, x and y. We also have a move method to move points. And finally, a draw method to show that points on the console. We then create a new instance with 1 and 2 coordinates and draw that point in the console. So by using reflection, we can add a new field to this specific instance without modifying the rest of objects, adding a new field set with the value of 3 and showing that new value in the console. We can also create a new function, draw third dimension, and add it later to that instance as a method and pass this message. And we can also modify the type or the class of all of the instances that in this case is adding a new message getX and invoking later with by using the point instance. So there are conceptual issues we have to tackle when we are adding a structural reflection to a class-based platform like Rotor. First, modifying the class structure has to implement the schema evolution approach that is based on if we modify the type of the class or type of existing objects, we've got also to have to modify the fields of the existing instances at runtime. For instance, if we add a new field, we have to define the default value of this field. And if we are working with code that use fields that does not exist anymore, that a special situation can be managed with runtime exceptions. So the main problem appears when we want to modify a single object and we don't want the rest of instances to be modified at runtime. So a good example is the implementation that has been done by some people called Metaxa that add a structural reflection to the Java platform. And they used the schema versioning approach that was based on adding a new class every time we want to modify a sole object. So the different problems have emerged. The first one is the class identity problem, that we have different classes but the same type. Also, of course, memory consumption problems. And class structure consistency, that modification of a version should be reflected on the rest of the versions of the same type. So these people abandoned the project, saying that the class-based model is not really suitable, it's not coherent with the structural reflective primitives. Almost all of the languages that offer structural reflective services do not use directly the concept of class. They suppress classes and they uniquely use objects. That model is called prototype-based model. We've got here an example with one class and an instance. This class has a shared behavior, draw and move, and a common structure with 2 coordinates. And this is one of the instances. If we want to model the shared behavior of a class without using classes, we can place the implementation of these methods in a single object that is commonly known as a trait object. Derived objects will inherit this shared behavior. If we want to represent this common structure, we can do it by placing this structure inside of a point, an instance that is normally called as a prototype with its default values. And every time we want to create a new instance of that class, we just have to clone the existing prototype. So prototype-based object-oriented model overcomes the schema versioning problem detected with classes. And it models the structural reflection in a coherent way. In this scenario, we can see how we have different instances of the same point class. If we want to modify the P1 object, we can place, for instance, a new attribute without modifying the rest of instances. At the same time, if we want to give a new message to the P2 instance, we just have to place that implementation inside of the slot of the P2 object. The rest of instances that do not understand this new message. Finally, we can also modify the behavior of the instances by placing the new methods inside of the trait object. So we've seen how a prototype-based object model overcomes the schema versioning problem detected with classes when we are using a structural reflection. But Rotor uses classes. And we must maintain the use of classes because first we want to adapt existing .NET applications, and second we want to make reflective languages interoperate with any .NET language. So what we have done is permitting the user using classes, but when he or she uses a reflection, classes will be treated as straight objects, and if he modifies the structure, we have implemented a lazy schema evolution for this type. And at the same time, objects are capable of grouping both attributes and methods. So what we are doing is implementing internally a prototype-based object-oriented model. So in this slide, I try to show the global architecture of the new reflective platform. Also, we have only worked here in the runtime environment and the BCL. We can see where we are looking for. For instance, we can take a C# application and compile it to an executable program and run it with the reflective rotor because we have extended the runtime environment. We have not worked in this level, but we think that it could be interesting in the future. Adding the capability of a dynamically typed language, for instance, C#, dynamic type and reflection at runtime. So these kind of languages could also be compiled and be executed with reflective rotor because we give support to reflection. And of course, any dynamic language that support or that offer the programmer reflective capabilities can also be compiled and executed by our new implementation. Finally, all of the applications could interoperate one with the other because they use the same type system and the same ion statements. So regarding with the implementation, we have two parts. First, a new set of primitives have been placed inside of the base class library. And second, we have modified the statements of the semantics of some IL statements to give support to this prototype-based model. So first, the new primitives has been placed inside of the structural namespace. A summary of the most significant primitives have been add, get, remove, alter, exist, fill to modify or inspect the structure of any class or any single object. We can do the same with methods, working both with classes and with objects and using static and non-static members. New methods can be created with the emit namespace at runtime. We also offer an invoke method that is pretty similar to the invoke method of the reflection namespace, but we have to take into account the new prototype-based model. And finally, we offer get and set value to know the value of fields at runtime in a statically typed way. A new version of the previous one that was written in Python is the one that we can see here. We have just used the BCL primitives. First, we create a set of field and add it later to an existing point. There is an instance. We can do the same with methods. We could generate a new draw 3D function and place to an instance and invoke it later with this primitive. And we can do the same with classes. We can add a new getX method to a point class, invoke it by using the point instance, and add a isShowing field to the point class. So the second part is modifying or extending the semantics of the runtime environment to give support to these reflective primitives. The benefits are that making any existing application adaptable, because we have modified the runtime environment, and the programmer need not to recompile the source code in order to make his code adaptable. And programmers should make no distinction between when he or she is writing adaptable or non-adaptable software, because we modify the semantics of some IL statements. So we have modified the just-in-time compiler, and the statements we have modified are those for loading fields, those for storing fields, and call and convert for message for calling methods. So implementation details. In Rotor, both classes and objects are instances of the object class inside of the object module. These instances has a fixed size data, we couldn't make these instances a variable size. So what we did is place the reflective informations inside of each sync block of the objects. So we have added to the sync block of each object two hash tables, one for attributes and for fields and the other for methods. So the reflective primitives must be supported in the statements we have previously seen. So what we did is add new semantics to a set of jitter functions and inside of the fastJIT module that are these that are shown in the first point. Anytime these statements are executed at runtime, they run runtime helper functions that we have also modified, these ones, and the rest of the implementation that of the services that access these reflective primitives has been placed inside of the BCL services that we've seen previously. So regarding to the performance assessment, we have divided our test into three parts. First, we have measured reflective primitives. Second, the cost of adaptiveness, trying to measure programs that do not use reflection at all. And finally, the benefits of using a just-in-time compilation comparing with interpreted-based implementations. So first, we have evaluated the performance on some reflective primitives in different scenarios and compared with CPython version 2.4 and ActivePython that are interpreted-based implementations of Python. We have also used Jython that generates Java code and IronPython version 0.6 that generates IL code for the .NET platform. Then we can see the results in this slide. We have two scales. The one on the right is the one used for IronPython and Jython. They are much slower than the rest. That is due to when they are using a structural reflection, they are generating extra code to simulate the reflective model inside or over an static platform like the Java or .NET platform. We can see how IronPython has not a continuous line. That is due to the version we have used has not implemented all of the services. Then we have ActivePython and CPython that are quite similar. CPython is a little bit slower. And our implementation, that is in yellow, is 5.74 times faster than the CPython implementation to execute these reflective primitives. We have to say that we have no support of all of the primitives of Python programming language, only reflection. The second part of our assessment was trying to evaluate the cost of using a structural reflection. So we've taken a benchmark, the Tonti benchmark, that does not use reflection at all. And we have executed the same C# code with the original SSCLI and our modification of Rotor. And we can see the results in these diagrams. We can see how in many of the tests we do not have a penalty cost, a performance penalty, sorry. And in the case of using files, hash maps, vectors, and string builders, we can see how our implementation is slower. So that is due to the significant loss of member accesses when we are not using reflection. What we did is evaluate exactly that cost. And we can see after many optimizations the results. In both cases, when we are using accesses to fields that has not been added with reflection, I mean they are static at compile time. And when we are invoking methods, we are 0.6 times slower than the original Rotor. We have also compared our implementation with two real C# application benchmarks that do not use reflection. In the case of an LR parser, we are 0.81 times lower and more than 2 times if we implement the compilation algorithm. And finally, the third evaluation is the benefits of using a just-in-time compiler to give support to those dynamic languages. So what we did here is translate the Tonti benchmark to Python and execute the benchmark with CPython and see the results. We've seen how our implementation is more than 9 times faster. And we can see also how in some cases Python is faster than our project. That is when we use files, hash maps, and vectors. We think that is due to the fact that Python includes these entities inside of the interpreter, and .NET offer these entities as a part of the BCL library. So this may cause a performance penalty. For instance, if we focused on array or matrix results, which are the same, we can see how in both cases are inside of the language, and we use 5% the time that is needed in CPython. So the major conclusions of our work have been that just-in-time compilation is a suitable technique to be used to support reflective primitives in dynamic languages. We are 9 times faster than when we are executing non-reflective code. And when we are executing reflecting primitives, we are 5.64 times faster than the fastest implementation. To make the CLI a dynamic platform to support these languages, the key idea is to extend the semantics of the runtime environment and execute in a native way. If what we do is generate extra code to simulate these services, this causes a performance penalty that we have seen in the case of IronPython and Jython. We've also have seen how a structural reflection is can be properly represented by using a prototype-based object model. And if we add a lazy schema evolution implementation, both classes and prototype-based languages can be supported. We also can modify any existing application because we have modified the runtime environment, so they use the IL statements. And finally, after many optimizations, we have reduced the performance cost of accessing members that have no reflecting from 350% to 60%. And we think that they can even be reduced more. Thank you very much. Probably have questions. Yes?
You modified the JIT to access the reflective structural modifications. Are those instructions aware that they are accessing new fields and functions as opposed to existing static functions and members?
Yes.
In case you can still do this,
Yes, what we did is actually modifying the code that the JIT generates. That is necessary because we have placed reflecting information in other places that the non-reflecting information has been placed. So we have to generate this new code to take this new information into account. And at the same time, what we did is modify the runtime helpers of Rotor to access this information, or even modify it if what we're doing is accessing with the new primitives inside of the BCL. More questions?
How does the prototype object correspond with the method tables and EE classes?
Yes. This is one of the most serious problems when we were working in this project, trying to think what is the mapping between those concepts. And this is what I've tried to show in this slide. We were thinking about giving a support to dynamic languages that, for instance, Python only offered the concept of class as a trait object without offering the structure. So the structure is only placed in Python inside of the object. But in Rotor, we have a class who represents both behavior and fields. So what we did is try to give support to all of the primitives, some for prototype-based languages and the other for class languages. So if you are in the higher level, for instance, in high-level languages, and you want to, for instance, give reflection to C#, you can modify a class like Python. If you are modifying methods, you are modifying the shared behavior. But what happens if we want to modify, for instance, fields of a class? what we did is implement for this special scenario a lazy schema evolution that is modifying in a lazy way the structure of the instances. But you cannot do that with Python because it's not a service of this language. But we want to give all the situations because we want to give support to this language or this language with reflection and even this one. But Python will never use that service because it's not part of that language. Okay. Any more questions?
Thank our speakers for this morning.